Hello everyone from Math 2000, Linear Algebra. It's Professor Winston here again with a video on your Zybooks section 7.1. It's on linear transformations between Euclidean spaces, right? So say between Rm and Rn, right? So these are going to be like functions where your input is a vector with, say, m components, and then it runs through a certain rule, a transformation, and your output is another vector, but from maybe Rn, maybe with n components, right? Some different number of components. So let's take a look. So like I said, it's like a function, right? So remember, in general, a function maps an element of one vector space to an element of another vector space. A mapping is also referred to as a transformation and can be used to manipulate an image. If an image needs to be enlarged or reduced, each vector in the original image can be scaled. An image can be rotated using a similar principle. These transformations, rotation, scaling, whatever, can often be represented in terms of matrix multiplication. Some linear transformations, again, they're functions, so they'll be given names like functions, see like t of x here. Remember like f of x from algebra, very similar. But now my input is a vector instead of just a single number. Some linear transformations, t of x, on vectors can be represented by matrix multiplication. A transformation represented by matrix multiplication has both properties of a linear transformation, which we'll get into later. And the standard matrix for a linear transformation can be found using the standard basis of the domain, right? Lots of words coming up here that we'll get into in a minute, right? When we talk about identifying the terminology associated with transformations, right? So we're doing functions, transformations from, say, Rn to Rm. Okay, so the other way around what I said doesn't really matter. We're going from one Euclidean coordinate space, vector space, to another Euclidean vector space. So a transformation generalizes the concept of a function. A transformation, t, from Rn to Rm, denoted with this colon notation here, the name of the function or the name of the transformation, t, then a colon, then your domain vector space, then a little arrow, and then the vector space that you're mapping to called the codomain. All right, not the range. Not the range. We'll get to that later. Because your codomain, you might not actually hit every single value, every single vector in the codomain. So this is a rule that assigns an element of Rn to an element of Rm. Like I said, the domain of a transformation is the set of all inputs. The codomain of a transformation, they should say it's the set of all possible outputs. Might not get them all, but it's what you're aiming for. Alright, so given a transformation from Rn to Rm, Rn is the domain, Rm is the codomain. And a transformation T is called an operator if the domain and codomain are the same. Right, so like from R to R or R2 to R2, then the transformation would be called an operator. Alright, and like I said, transformations are usually defined by vector-valued functions. Right? So every component of the output is some function of the components of the input. Then the vector t of x, which is going to be in the codomain, right, the output set, for a given x in the input set, right, a given x in the domain in this transformation, is called the image of x under T. And then you go the other way around. Take a vector from the codomain. The pre-image of a vector from the codomain under this transformation T is all the elements of the domain that map to it. All the elements U of the domain such that T of U would be equal to that vector from the codomain V. And finally, the range, right? The set of all elements of the form T of x, where x is in the domain, for a given transformation is the range. So the set of all actual outputs. The codomain is the set of where all the outputs live, but not every value in the codomain is an output. The range is the set of all the actual outputs. Right? So the range is actually a subset of the codomain. Right? So it may be smaller, but it could also be equal. So for instance, and I'll write this up on some paper and show you the use of some of these words. Okay, so here we have a transformation called T from R2. So vector, my inputs will be vectors with two components, see x1, x2 here, to R3. So my outputs will be vectors with three components, as you're seeing over here on the other side of the equal sign. Right. Now, just using some of the words that were thrown out here, the domain of this particular transformation is R2, right, where all the inputs are coming from. Right, that's that set. The codomain is the set where all the possible outputs come from, and that's this set here, R3, right, vectors with three components. And then here's your rule. Right. Now, they're giving us a vector from the domain. So suppose x vector x is the vector 3, 1, and this belongs to R2, right? It belongs to the domain. Say I want you to find the image, right? The image find the image of this vector, of this input vector, under T, right, under this transformation T. Well, let's just simply find the output. Right? The image of an input vector is the output when you plug that in. So let's apply this rule. So T of vector 3, 1 is equal to, and then just getting this output vector with three components. And you see I'm replacing every x1 over here with 3, and replacing all the x2s with 1. So we have x1 plus 1, or 3 plus 1, which will simplify. Second component, 2 times x2, so 2 times 1, right, 2 times x2. Third component, x1, 3, plus x2 is 1. So the image of 3, 1 under this transformation T is this vector from R3 with components 4, 2, and 4 again. Right? And this belongs to R3. But this would be considered the image of vector 3, 1, this vector 4, 2, 4. Right? And then another thing we could say, related to some of the words we saw, is that the vector 3, 1 is in the pre-image. So this vector 3, 1 is in the pre-image. of the vector 4, 2, 4. Because again, the preimage of some codomain vector is all the vectors that map to it. So right now we only know that 3, 1 maps to 4, 2, 4. But there may be some other ones, right? There might be some other vectors in the preimage of 4, 2, 4. But really, it would have to be 3, 1. Actually, 3, 1 would be the only vector that would map to 4, 2, 4 here. Right. Additionally, we could also say this. We could say that 4, 2, 4, right, this output is in the range of T. Right, the set of the actual outputs, the actual values or vectors that get mapped to. Right, so lots of, just me using the words that have popped up here. So again, domain, input, set of inputs. The codomain is where the possible outputs live. You have a rule describing how to take an input to an output. If you're given an input vector, if you're given a vector from the domain, the image of that vector is simply the output when you plug it in. And the pre-image of some output vector is all the input vectors that map to it. So again, this vector here is one of the vectors. Again, it's probably the only one. I think it's the only one, but there might be other ones. But this vector we've seen here is in the pre-image of that output vector, 4, 2, 4. And any vector that is an actual output, like 4, 2, 4 is, would be in the range of the transformation. So again, just so you get the terminology, seeing it used at least once. And I explain all that here. All right. So again, all you're doing in this first activity is plugging in values. So here's a transformation from R2 to R2, which would be called an operator. All right. Remember, if the domain and codomain are the same, you could also call the transformation an operator. So my input is see a vector with two components, 1 and 1, and the output is this vector with two components, and again they describe to you how to find it. So here my x1 and x2 are both 1. So the output, the first component would be 1 times 1, which would just be 1, and that's all I'm asked to fill in, because they already gave me the second component, right, which would be 1 squared plus 1 squared, which is 2. So real simple stuff here. Just plugging in values, making sure you plug in the correct component that they want. Alright, so I'll leave those other two to you. So here we have, just use of the terminology. So T is a transformation from, R4 to R2. So my inputs are vectors with 4 components. See this x1, x2, x3, x4. My output is a vector with 2 components, which you're seeing on the other side here, the right side. So, what's the domain of this transformation? It's R4, right? So I just slide R4 into this first slot. Well, if it'll work for me. There we go. And what's the codomain? It's R2. The range is just, a description of all the outputs, which this little box is here. Right, that describes all the outputs, that showing you how to find all the actual outputs using this rule. So the range of T is just a description of the outputs. And then what's the image of this input vector 0, 1, 2, 3. So I plug in 0, 1, 2, 3 for x1, x2, x3, x4. So 0 plus 1, 1, and then 3 minus 4, negative 1. So 1, negative 1 is seen here as the output or the image of this vector under this transformation. Pretty simple stuff, I feel. And the challenge activity. Now this first one, they're just asking you for the proper dimensions. Look at this rule here. The input is from R3. Right, the input has 3 components. The output has 4 components. So this would be from R3 to R4. That's all I'm has to fill in. Here, you're given the rule. You're given an input. What's the output? So replace x1 with 4, x2 with negative 2 over here. You get your 3 components. And pretty easy. And same here. But you have to fill in, what's the domain dimension, what's the codomain dimension, and then when you plug in this value, what's the output? When you plug in this vector, what's the output vector? Very simple. Alright, now, these transformations we've been looking at, like in this activity here, this example here, some of them are considered linear, and some of them are not. That's what we're going to get into now. What makes a transformation a linear transformation? All right, so a linear transformation is a transformation that preserves the following properties for all vectors u and v in the domain of T and all scalars R. Right? So remember, we'll just consider the field of scalars to be the real numbers here. We'll say R is any real number. So for any vectors u and v, T of u plus v will be equal to T of u plus T of v. And T of R times v will be R times T of v. Now putting these together basically tells me that any linear combination in the domain is going to be the same linear combination of their outputs. It's going to be preserved in the codomain. That's what they mean by preserve the properties of additivity and homogeneity. All right. And I'll tell you right now, I'm going to show you how to check these properties, but a quick shortcut for you. Look at all the components of the output. If every component of the output is simply a linear combination of the input components, then it's a linear transformation. So see how my input components are x1, x2 here? And then the first component of the output is 1x1 minus 1x2. That's a linear combination of x1 and x2. The second component is 0x1 plus 1x2, another linear combination of these two components. So you're going to see that this first one is a linear transformation. Whereas the second one, see the first one, x1, that's 1x1 plus 0x2. That's a linear combination of x1 and x2. But the second component in the output, x1 times x2, that is not a linear combination of x1 and x2. Remember, a linear combination is a scalar times one of them plus a scalar times the other. So you're going to see that S is not a linear transformation. But I'll go over on paper and show you how we're going to demonstrate, whether or not a transformation is linear. So I'm going to go to a piece of paper and I'll do part A first and then part B. So here is part A of that example. We have T of, x1, x2, so something from R2. This is from R2 to R2, right? 2 component input, 2 component output. And we're asked, is T from R2 to R2 here, is this operator, this transformation, linear. All right. So in order to be, a linear transformation satisfies those additivity property and homogeneity property that were mentioned. So first I'm going to let u and v be vectors from R2 from the domain. Okay, these are vectors from the domain R2. And R be a scalar, right? So just be a real number, right? Just one of any scalar. So U, let's say, has components U1 and U2, and V, let's say, has components V1 and V2. All right, so the first check, the additivity property. Additivity. So the big question here is the value of t at u plus v always going to be equal to the value of t at u plus the value of t at v? And so it's almost like you're distributing the t, even though it's not distributing, okay, but it looks like it. So applying the transformation to u plus v gives you the same result as if you apply it to each of the vectors separately and then add them. Right. So what I like to do is look at one side then the other and see if we end up getting the same expression. So let's take a look at the left side. So t of u plus v. Well, that would be t of, this is, they haven't mentioned otherwise, so we're going to assume here that vector addition is the usual vector addition in Euclidean spaces. So u plus v, if I set them up the way I had them here, that would be u1 plus v1 for the first component, u2 plus v2 for the second component. And then I'll apply, so this is add them first and then apply t. So I added the vectors first, and now I'm going to apply t. Now, when I apply this rule to this vector, x1 is now u1 plus v1. x2 in my input is now u2 plus v2. So I just make those replacements over here. So x1 is u1 plus v1, and then minus x2, u2 plus v2, and then the second component of the output is just x2, which is u2 plus v2. And I guess if you'd like, we can distribute this negative here. And I'm getting this expression as an output, right? u1 plus v1 minus u2 minus v2. And then this is the second component, right? u2 plus v2. Okay. Alright, so that was the left side of this. Now, I'm going to do the right side and see if I get the same expression. See if they're equivalent all the time. Right. So here's the right side. So I take a look at t of u plus t of v. So this one, you apply the rule to the vectors first and then add. Whereas, this one you added first and then applied the rule. All right, so this would be t of, vector u is u1, u2, plus t of v had the components v1, v2. And now I'm applying the rule to these two, right? So apply the rule to u, just replace x1 with u1, x2 with u2. So this is u1 minus u2 for the first component, and then u2 for the second component. plus, and then applying t to v, the v1, v2, v1 minus v2 for the first component and v2 for the second component. And then can you see how if I were to add these together, I'd get exactly what I got earlier? You'd have u1 minus u2, well there's u1 minus u2 there, plus v1 minus v2, plus v1 minus v2. So the first components would be the same, and then you got u2 plus v2, there's u2 plus v2 in the second component. They're exactly the same expressions. So yes, for any vectors in the domain, you could take any pair of vectors from R2, and the answer is yes. T of u plus v will be equal to t of u plus t of v. Right? So that additivity is preserved by this transformation. All right, so that's just part one, though. Right, you have to show both. You have to show that additivity holds, as well as the homogeneity, right? With the scalar multiples. So step two. So answer to question one was yes. Question two. Does this transformation, right, that I have written here, does this preserve that homogeneity property? So the question here is t of r times u, again r is any scalar, u is any vector from the domain, is this equivalent to just pulling the scalar out, r times t of u, for all vectors in the domain u and all scalars? So same thing as I did before, I'm going to just work with one side at a time and see if I get the same thing. So I'll start with that left side. So it's t of r times u. So this is multiply the vector by the scalar first, and then apply the rule. So this would be t of, now r times u, and again they haven't defined scalar multiplication in some weird way, right? So we're going to assume it's the typical scalar multiplication for Euclidean vectors. If I take r times vector u here, my components will be ru1 and ru2. And then if I apply the rule, right, apply this rule to this vector, x1 is now ru1, x2 is now ru2. So we have x1 minus x2, or ru1 minus ru2, and then x2, which is now just ru2. Okay, well, that's pretty simple. All right, now let's look at the right side and see if I get the same expression, the same output. All right, so the right side looks like this. You have r, scalar r, times t of u. So this is apply the rule to the vector first and then multiply by the scalar. So this is r times t of u1, u2. So I have r times, and then I apply the rule. You have u1 minus u2, and then u2. Now, can you see if I did this application, these would be the same, right? If I multiply this first component by r, you'll have ru distributing, you'll have ru1 minus ru2, exactly the same. And then the second component, ru2, exactly the same. So these are the same thing, these are equal. So the answer to that homogeneity question is yes. T of any scalar r times any vector from the domain u will be equal to, all the time, r times t of u. And since both the additivity and homogeneity properties hold, that means that t is a linear transformation. since both hold. Okay. All right, now I'll pull up the second part of the example, and we're going to see how it's not a linear transformation because one of these properties does not hold, or both. I mean, but as long as if one of them fails, if it's not additive or not the homogeneity property doesn't hold, if one of those properties doesn't hold, it's not linear. Okay, so here was part B, this transformation called S. And it's from R2 to R2 again. You see my input has two components, output has two components. And again, the question is S, right, this transformation from R2 to R2, this operator, linear? Is it a linear transformation? So again, I have to go through both properties. Now again, if the first one fails, I don't need to go through the second one. Right. So additivity, right, is S, and again I'm going to use the same U, V, and R from earlier, right? Because these are vectors from R2 again. So is S of U plus V equal to S of U plus S of V? And this is for all U and V from the domain. Alright, so just like before, let's take a look at the left side and the right side and see if I get the same expression. And if I don't, then I'll try to find an example of when they're not equal, right? Find a counter example. You should be doing that to show that this is not true all the time. Alright, so we have S of, now again, I'll just do the U plus V right now. That would be U1 plus V1, U2 plus V2. And applying this rule to it, remember x1 here is now U1 plus V1. x2 is U2 plus V2. So I'm getting U1 plus V1 as the first component, and then U1 plus V1 times U2 plus V2. They're being multiplied. And I'll actually simplify this. This is U1 plus V1 in the first component, and then U1 times U2 plus U1 times V2 plus U2 times V1, doing foiling here, plus V1 times V2, 4 terms there in that set. This is all the second component. Alright, well now let's look at the right side. S of U looks like this, S of that's U1, U2, plus, and then S of V, right, so V1, V2. Alright, well this is, if I apply the rule to U, I'm going to get U1, and then U1 times U2, plus, and then I apply the rule to V, get V1, and then V1 times V2. And then putting these together, I'm getting U1 plus V1 for the first component, and then U1 times U2 plus V1 times V2 for the second component. These are not the same. The first components are the same, sure, both U1 plus V1, but the second components are not necessarily equal. Yeah, they got the U1 times U2, they got the V1 times V2, but what about these terms? U1 V2 and U2 V1. These are not necessarily going to be equal all the time. And if that's the case, let me just show you an example. I'm going to show you an example. I'll find a vector U and a vector V where this does not happen. So here's an example or a counter example. Suppose vector U is the vector 1, 2. And the vector V is the vector 3, 4. Why not? Well, S of u plus v, right, the left side, would be S of, and then, this is adding the vectors first. So I'd have the vector 4, 4, 6. And if I apply this rule to the vector 4, 6, I get first component 4, second component would be 4 times 6, 24. All right, so that's what I get with u plus S of u plus v there. Now the other side is S of u plus S of v. Well, if I apply S to u, all right, to 1, 2, I'm going to get 1, 2 again. All right, 1 for the first component, and then 1 times 2 for the second component. And then I apply S to v, apply this rule to v, going to have 3 for the first component, and then 3 times 4, which is 12 for the second component. Add these up, and you're getting 4 for the first component and 14 for the second. Not equal. These are not equal. And all you need to do is show me one example to show that that rule does not hold for all vectors from the domain. So, the answer to my question, is this true? Does this additivity property hold for all pairs of vectors from the domain? The answer is no. All right. And again, the reason I can show you why with one example right here. That additivity property doesn't hold. Therefore, S is, it's a transformation, sure, but it's not a linear transformation. All right. And now, if it were additive, if the additivity property worked, then I'd have to check that homogeneity property. Both of them have to work in order for the transformation to be linear. All right. So I'm going to watch them go through this thing here. Cool. And then again, you're asked to determine whether certain properties hold for certain transformations. So I'm given these transformations, these operators from R2 to R2. Here's T of x and S of x. Now, I'll tell you right now, like I said, if every component is just a linear combination of the input components, if every component of the output is just a linear combination of the components of the input, it's going to be linear. So S will be linear, T will not be, cube root and stuff, and cube powers and all that. This isn't going to be linear. Yeah, this definitely won't satisfy the additivity property. All right. Now, because this is the cube root of a couple cubes, it will satisfy the homogeneity property. Because if I replace x1 with, 2 rx1 and x2 with rx2, you'd have r cubed here, come out, cube root of r cubed would be r, you'd have r times the top, pull that out, r times this, pull that. T would satisfy the homogeneity property, but not the additivity property. So it's not linear. Right? T is a linear transformation? No, it is not. Now I already told you S is going to be linear, so it'll satisfy additivity, it'll satisfy homogeneity, it is going to be linear. Right? And again, you can verify that the way I did it on paper earlier. Gosh darn it, stop jumping around. All right. Now, if you have a linear transformation, then you can write the transformation as a what's called a matrix transformation. All right, and a matrix transformation looks like this, where T of x is some matrix A times that same input vector x, right? So the output is just the input vector times a matrix. And that matrix is going to be called the standard matrix for the transformation. So for instance, I'll write this one up here. on paper and show you how to. So here was the transformation we're given. Now I'm going to tell you right now, and you can hopefully see it based on what I was telling you earlier. So my input's going to be from R2, right? This is a transformation from R2 to R3, right? The output has 3 components. My input components are x1, x2. See how every single output component is just a linear combination of the input components, right? A number times x1 plus a number times x2, every single one of these. So T is a linear transformation. And that means, and this goes in both directions too, this goes both ways, that means T is also a matrix transformation. That means that you can write T of x as some matrix times that same x. Right. And it's very simple. You've seen this before in solving systems. If I see something like this, this is a 3 by 1 column vector here, right? 3 by 1, 3 rows, 1 column. I can express this as a matrix where down the first column I got the coefficients of x1, down the second column I got the coefficients of x2, multiplied by that input vector, x1, x2. This here is the matrix A that's being talked about. And you see it's a 3 by 2 times a 2 by 1 would be a 3 by 1. You see how the transformation takes my input vector and its output is that same input vector times some matrix on the left. All right, and this is called the standard matrix. This matrix, this 3 by 2 matrix here with 4, 6, 2, -7, and -3, 5 rows. This would be called the standard matrix for T. Right. Very easy. Very, very easy in my opinion to find the standard matrix of some linear transformation. And they show you that same thing here. And then if you wanted to find an output, see they plug in 2, -3. You could plug it in up here if you want, or just take 2, -3 and multiply it by this standard matrix and get your output vector. Very simple. All right. So again, very easy here. Just all these are all linear transformations. Right? The only transformations you can express as matrix transformations are linear transformations. Right. So the first one, you see the coefficients of x1 are 2 and 0. The coefficients of x2 are 0 and 3. So 2, 0, 0, 3. This matrix here would be the standard matrix for that transformation. Let's slide it down here. And good. Right. And again, just 3, 1 down the first column, -1, 2 down the second column. So this one here. Right. This one has only 2 variables. We got 1, 3, -2, 1, -3, 1. And 1, 2, -2, 1, 4, -1. Right. Really, just like a coefficient matrix is your standard matrix for these linear transformations. Very, very easy. And because of those properties earlier for a linear transformation, right, the additivity property and homogeneity properties, right, these two here, a lot of other properties follow from these, which they're getting to down here. If you have a linear transformation, right, or a matrix transformation, right? Remember, every matrix transformation is linear. Every linear transformation is a matrix transformation. So they're kind of used interchangeably. the zero vector in the domain will be mapped to the zero vector in the codomain. This is just the homogeneity property, and these are basically the additivity properties. So, yeah. So let's see here. Yes. Oh, well, okay. Now, this goes one direction. If you have a linear transformation, the zero vector will be mapped to the zero vector. That does not mean that if the zero vector maps to the zero vector, you're going to have a matrix transformation. That does not mean that at all, right? Because remember, a matrix transformation is linear. You can get there are non-linear transformations out there that map the zero vector to the zero vector. So just because the zero vector maps to the zero vector doesn't mean the transformation is linear. Right? Like they give you an example here. Right? Here's a non-linear transformation where the zero vector in the input would map to the zero vector output. If T is linear, well, I already said this. If T is a matrix, then T is linear. Again, it goes both ways. If T is a matrix transformation, then T is linear. If T is linear, then T is a matrix transformation. Is this linear? No. Sure, the second component is a linear combination of these three. Right? You have 1 of x1, 0 of x2, 1 of x3. But the first component is not a linear combination of these three. Right? You got just a number 1. That's not a multiple of x1, x2, or x3 here. So this is not linear, and if it's not linear, it's not going to be able to be expressed as a matrix transformation. All right, and then finally here we got. Now I showed you a very easy way. You saw finding that standard matrix for a linear transformation is very simple. But you can also use. You can also use the standard basis vectors for the domain to also find the standard matrix. And let me show you that same example here. So I'm going to go back to a piece of paper. And this is that same example. Okay, we're asked to find the standard matrix, but using the standard basis vectors of the domain. All right, so I'll refresh your memory. Here was the transformation, and the standard matrix was this 3 by 2 here. Let's find it another way. All right, so my domain, the domain for this transformation is R2. And hopefully you remember what the standard basis, was that fancy E with a subscript of 2. This was remember the standard basis for R2. Were just those vectors 1, 0 and 0, 1. Sometimes referred to as just vector E1 and E2. All right. So another way to find the standard matrix for a transformation, a linear transformation, is to find the images of the standard basis vectors. So what is T of 1, 0? Well, just go through, replace all the x1s with 1 and x2s with 0, and I'd get 4, 2, negative 3. And this is going to be the first column of the standard matrix. So the image of the first standard basis vector is going to be the first column of the standard matrix for the transformation. And then the same thing goes for the second standard basis vector. What is T of 0, 1? I'll plug in 0 for x1, 1 for x2. You get none of these. All these are 0 now, and you just get the vector, the output of 6, negative 7, 5. And this image of the second standard basis vector is the second column of the standard matrix. So the standard matrix of T of this transformation, which I'll call A, has a first column of 4, 2, negative 3, and a second column of 6, negative 7, 5. And there we go. And that's exactly what we got earlier. Just pulling out the variables, writing like a coefficient matrix. All right, so this is just an alternate method for finding the standard matrix of some transformation. Now they go into a nice example of where this will be useful. Talking about transformations on the plane, moving one vector to another vector on the plane. So for example here, they asked to find the standard matrix for the projection transformation of a vector along a line through the origin in terms of theta, where the theta is the angle that the line makes with respect to the horizontal axis. And it says use the standard matrix to find the projection of the vector 4, 8 onto this line, or onto the line that makes a 30-degree angle with the x1 axis. So I'll draw a picture of what's going on here, what this transformation is. So we have our xy plane, or x1, x2 plane. So say here's the x1 axis. They're calling it x, usually the x-axis, and then the x2 axis. Right? And we've got a line that forms some angle of theta. Right, so here's this line that forms an angle of theta with the x1 axis. Right. Now what we're trying to do is figure out, if I were to take any vector, take any vector from R2, this is R2 here, right, 2 dimensions. So if I were to take any vector, say V here, they're asking us to transform it by, this is the projection transformation. Now you've seen vector projection before, right? I take this vector and I project it to this line, and that creates this new vector, right? So this is the projection, onto the line of vector V. Right? So my input is a vector from R2, and my output is going to be some vector on this line, right? The projection vector that's going to be on this line. All right. Well, I'm going to draw this picture again because, now you could do it, but it's kind of difficult to take a general vector here and figure out what's going on. What's the rule that projects me onto a vector on any line, right? Some line that forms an angle of theta with the x1 axis. So I'm going to draw this picture again. Okay, we have our x1 axis, x2 axis. And again, there's this line going through the origin that forms an angle of theta with the x1 axis. Now, if we want to project onto this line, projecting onto this line would be like projecting onto this vector. Right? So I'm going to pick a vector here, a vector on this line, and I'm going to call it U for a unit vector. Let's say that just to make it easy, unit vectors are easier to work with because they only have a magnitude of 1. And if this is the case, if I have a vector here starting from the origin that's a unit vector, and it forms an angle of theta with the horizontal axis, well then we know the components. All right, that means that vector U here has components, the horizontal component would just be, if the length is 1, so like this is the hypotenuse of a little right triangle I got going on here. The horizontal component would just be the cosine of the angle formed with the horizontal axis. The vertical component would be the sine of that angle. Right? And so if we want to project any vector onto this line, we're basically going to be projecting the vector onto this, the line, it's the line containing this unit vector here, this cosine theta, sine theta. Right. Well, instead of looking at just any old vector, let's look at what happens when I project the standard basis vectors onto this line. So remember, the standard basis vectors are 1, 0. Right, so let's say this is 1, 0 here. Let's call it, this is E1. So remember, E1 is the vector 1, 0. And E2 is, this vector here, the other standard basis vector. Right, these are 1 unit right, 1 unit up. And what I'm going to do is I'm going to project E1 onto the line, project E2 onto the line, and those projections will give me the columns of the standard matrix for this transformation. Right. So what's the projection? So 1. What's the projection of E1 onto U? Remember how this goes. Right? Hopefully you remember vector projections. This was E1, dot U divided by U dot U and then times U. Right. Now, E1 dot U. When I dot these, right, you just do 1 times cosine plus 0 times sine. That's just cosine theta. And then I set it up so that U dot U was 1. Right? I had U being a unit vector. So this denominator is 1, and then U is the cosine sine, right? Cosine theta, sine theta. So this first projection, the projection of the first standard basis vector onto this line is cosine squared theta, and then cosine theta, sine theta. All right, and this is going to be the first column of my standard matrix when I write the transformation out in full later. I'll say first column. Right. Then 2. What's the projection of the second basis vector? Right, 0, 1. I didn't write it, did I? This is 0, 1. What's the projection of the second basis vector onto this line with the vector U? So again, that'd be E2 dot U over U dot U times U. Well, U dot U is going to be 1, and E2 dot U is just sine theta. Right? So this is sine theta times vector U times the cosine theta, sine theta, and putting the sine theta in, we get this is our second column. So cosine theta, sine theta, and then sine squared theta. And this will be the second column. And now I can write my transformation. Right, so now the transformation, this projection transformation, the projection onto a line. Again, I'll call it T. We're going from R2 to R2. Does this. T of any vector then, say x1, x2, is going to be equal to this standard matrix with these columns. First column, cosine squared theta, cosine theta, sine theta. Second column, we got from the projection of the second basis vector, cosine theta, sine theta, and then sine squared theta times x1, x2. There's our transformation. And it would be linear, right? If you take projections of vectors, a vector projection, additivity and homogeneity would be preserved, and you could verify that on your own. I'm not going to do that here. I don't want to waste any more time. Well, okay, now let's use this. Let's use this in the activity. Right, this projection, now they go through all this here. Alright, get the same thing I showed you. Let's use this in this activity. Alright, so say let T be an operator on R squared that projects a vector onto a line L, which makes an angle of 60 degrees. So I'm going to replace theta with 60 degrees here with respect to the horizontal axis x1. What is the unit vector v in the direction of L? Oh, okay. Well, that would just be cos. I already did that. This isn't anything yet. They haven't totally finished it. But what would be the unit vector v in the direction of L? All right. So if I look at my paper, that'd be that vector u they're talking about here. All right. If this is the line and this is 60 degrees, the unit vector that's in that direction would be the cosine of 60, sine of 60. Now the cosine of 60 was a half. Sine of 60 was square root of 3 over 2. Alright, now square root of 3 over 2, thinking back to your trig, square root of 3 over 2 is about 0.86 something. Oops. Square root of 3 divided by 2. Yeah, 0.866, so approximately 0.87 if I round to 2 decimal places, right? So here, 0.87. Okay. And then they're making the first column and second column. All right, they're making the first column and second column of that standard matrix. So again, going back to what I wrote, the first column is just going to be the back here, first column of the standard matrix. This is that projection of E1, the projection of the first standard basis vector onto the line. And if I replace theta with 60 degrees, or cosine 60 is a half, so this would be a half squared or a quarter. And then you have down here a half times the square root of 3 over 2, which is, they already gave us this 0.44 here, but the first one's just a quarter, right, 0.25. And then what would be the second column? All right, the second column, now they gave us the second component. It would be the same as the second component of the first one. It would be cosine 60 times sine 60. So a half, it would be the square root of 3 over 4, or 0.44. Right. And finally, what would be the projection of the vector 5, negative 3 onto this line? Right, so then I take that standard matrix. All right, so I guess I take this is the first column, this is the second column, and multiply it by the vector 5, negative 3. Now they gave me the first one there. This. So I'll write out what's happening. All right, I'll write out what's happening here. So we had, if theta was 60 degrees, our transformation would be, they said it was a 0.25, 0.44, 0.44, 0.76, the rounding the decimals, times vector x. And we're asked to figure out what would be the projection of the vector 5, negative 3. So I'm taking this matrix, this standard matrix, and multiplying it by my input vector. All right, so this would end up being a 2 by 1. So again, I think they already did the first one. All right, that would be 1.25, then minus 1.32, so negative 0.07, and they already had that. All right, they already had that on the in the answer for the activity. All right, then 5 times 0.44, that'd be 2.2. All right, 2.2 minus, minus 3 times 0.76. So it's 210 plus 18, 228. So negative 2.28. So negative 0.08 for the second component of the projection. If you use those numbers from the previous two results. Great. Yeah, so they're just putting this together, replacing theta up here with 60 degrees and rounding it everything to 2 decimal places. All right. So that was a lot, but still doable. Then finally you got your additional exercises. Great. All right, so some of these are in your homework, some of them are not. I would still recommend trying them all, just to get more exposure to the material, get better at it. I wouldn't worry so much about this projection stuff. I don't think I asked you about it, but they do have a question at the end about projections. So if you want to take a look at that, just replace theta with 45 degrees up there and do the same thing. And you can always check the solutions too. But please, try to work things out beforehand before you go looking at solutions. And of course, if you have any questions, send me a message. I'll get back to you as soon as I possibly can and try to help you out. Hopefully this video helps you when you're working on this stuff on your own. And thank you very much for watching.